everyone. So in our last video, we focused on getting information about a function by looking at its graph. Specifically, we learned in the last video how to find the domain and range of a function from its graph, as well as solving inequalities using a graph. So in this video, we're going to be focusing on a couple of other sort of features that you can read by looking at the graph of a function. So the first one is going to be whether the function is increasing or decreasing, and that we'll learn what that means in a moment. And then later in the video, we'll talk about a type of feature of a graph that is called a local maximum or local minimum. So I'll remind you of this later, but when you hear, you might notice I say maxima, minima. That's just the plural of maximum and minimum. Okay, so let's get into what I mean by increasing and decreasing. So the definition of a function increasing and decreasing is pretty much exactly what I think you'd guess. So a function is increasing if kind of reading the graph from left to right, if the graph is going upward, right? And the word I'll write down is if the graph rises, but rises just means kind of is going upward. If its graph rises from left to right. Because, you know, when we're reading a graph, you should be kind of going from left to right, right? Because that's how the number line works. And so what might an increasing function look like? Well, it could look something like this. This would be an example of a function that is increasing because as you move from left to right, we see that the graph is going upward. So now let's write down the definition of decreasing, basically what you would expect. So a function is decreasing if its graph falls. So falls meaning it kind of goes downward from left to right. And so a function that is decreasing might look something like this. That would be an example of a function that is decreasing. So this is something we'll talk more about in our next video. So our next video is going to be basically kind of a review of the topics we learned in the last video and this video, but in the context of kind of like real world situations. So we'll get more into what I'm about to say in the next video. But I think one helpful way to kind of make sense of the topics in today's video is to imagine that the function represents some kind of a real world situation. So for example, if these graphs, the green and the red graphs I just drew, let's say that they represent the temperature of a particular place as time goes on, or the population of a particular place as time goes on. So if the graph is going up, that would mean that the temperature or the population is increasing, right? And if the graph is going down, that would mean that the population or the temperature is decreasing. So that's one way you can kind of intuitively make sense of what we're talking about with increasing or decreasing. Okay, so these graphs that I sketched here, right, these are examples of functions where the whole function is increasing in the first one, right? And in the second one, the whole function is decreasing. But for most functions, they're going to be doing some kind of a combination, right, of increasing and decreasing. So most functions, or I'll say many functions, include both increasing and decreasing parts. And so what we're going to be doing in this video is basically looking at a function that has parts that are increasing and parts that are decreasing, and we're going to be able to describe where are the parts of the graph where it's increasing, where are the parts of the graph that it's decreasing. And so importantly, what we're going to be doing when, you know, if we're describing where is the function increasing and decreasing, the answers we're going to be giving are going to be intervals of x values. And so I'm going to write that down, and then you'll see what I mean when we get to an example, but I just want to write it down explicitly because it is a really important thing. So we can describe the locations of the increasing and decreasing parts using intervals of x values. So you'll see what I mean by that when we look at this, this example. Okay, so first example, so this is going to be some kind of a function, f of x. We don't need to know its formula in order to do this. We just need the graph. And so the question we're going to answer is we're going to answer on which intervals is this function increasing? And then next we'll answer on which intervals is it decreasing. So the first thing you want to do when you're answering a question about, where is a function increasing or decreasing is kind of like highlight for yourself, whether you actually write it down or just kind of mentally highlight the parts of the graph that look like they're increasing. So we want to kind of just scan along this graph from left to right and see, where is the graph going upward? Where is it going downward? So this part of the graph here that I'm tracing over is increasing, right? As we move from left to right, it's getting bigger and bigger. It's going upward. Now, notice that at x is equal to -1, the graph kind of flattens out. And so I'm going to put like an open circle here. That's not meant to suggest that there's no point there. I just want to emphasize the fact that at that value, at x is equal to -1, the function is not increasing or decreasing, right? It's flat. And so we want to make sure that when we write down our intervals, we don't include those like transition points. Okay, so let's continue to draw some stuff on this graph. So what's happening next? Well, next the graph is going downward, right? So starting at -1 or starting just after -1, the graph starts to go down. So it's decreasing, decreasing, decreasing. And then at x is equal to +1, again, the graph is neither increasing nor decreasing, right? It's like just flat. It's kind of in the process of turning around. And then what happens starting after x is equal to 1? Well, now the graph is going up again. So what we can see is that we have 2 increasing parts and 1 decreasing part. And I'm going to add some arrows here just to remind us that actually the graph is going to keep going. So it's actually going to, it's increasing even before we see the graph, and and it's also increasing even after the graph ends. Okay, so now let's go back to this question. So it's saying, on which intervals is f of x increasing? And so the really important thing that I already wrote down above is that when you see this phrase, on which intervals, you should always be giving x values. Always. That's like the biggest mistake that students make on these type of problems is they'll identify the correct part of the graph, but they'll give me y values. And so I'll explain in a moment why it's important to give x values. And then I think, again, in the next video, we'll really be able to make sense of like why it makes more sense to give x values than y values. But yeah, so let's look at this green part of the graph that I highlighted. So how would we describe this green part of the graph using interval notation? And referring to the x values, well, again, the graph continues off the page. And so the beginning of the interval is actually -infinity, right? We don't have like an initial point where the graph starts increasing. If you were to keep going, the graph still has the shape of increasing all the way up until -1. And so we say -infinity to -1. And now notice that I didn't include -1. And again, that's because at -1, we have a turning point. At -1, it's neither, I'm just going to say neither, it's neither increasing nor decreasing. And then same thing we'll see here. And so we're not including that endpoint because that is not a place where it's increasing, right? It's not actually increasing at -1, it's doing neither. Okay, so what's the next interval where this function is increasing? Well, it starts at x is equal to 1, but again, we want to make sure that we don't include 1 because that is a turning point. That's a place where it's not actually increasing or decreasing. And then we can see that the graph continues to travel in the same direction off of the page, and so it continues to increase. So those are the intervals where f of x is increasing. Okay, so now we can answer the opposite question. So on which interval is f of x decreasing. So again, now we're just looking for the portion of the graph where it's going down from left to right. So we already highlighted that in red, and we just want to record the x values where this is happening. So it starts decreasing at -1. Again, we're not including -1. And then it stops decreasing at 1. So I'm not going to write down the not included part again, but just, be aware that that's going to be the situation always. So again, two most common mistakes students make on this topic is either instead of writing the interval as x values, writing it as y values. So for example, maybe for the first interval, writing it instead as -infinity up until 2, right? That would be if you were keeping track of the y value instead of the x value. So that would be wrong. The other mistake that I see students making is including the transition point. So just make sure you don't include that. Okay, so I just want to briefly mention, I think one way you can make sense of, why is it that your answer is x values? And again, I think this will make more sense when we do an explicit example in the next video. But for example, imagine that, again, this is some kind of a graph representing temperature, and it doesn't really make sense because it includes negative x values, and negative time doesn't really make sense, but just bear with me for a moment. So imagine that this is a graph that is recording the temperature of a particular place as time goes on. So you can think of this question, on which intervals is the function increasing? Think of that as being like, during what time period is it increasing? Right? If someone said, when is the temperature increasing, you wouldn't be giving outputs, you'd be giving inputs as your values, right? Because time would be like the input values, and then the temperature would be the output values. So yeah, I think everything I'm saying now, I think if you're confused, just wait till the next video, because we'll really make that explicit in the next video. But I just want to kind of give you a little idea of why it is that we're giving x values instead of y values. And yeah, I guess more generally, it's just x values are really our method for describing where or when something happens. So similarly, like in the last video, when we were solving inequalities, or if someone asks you for which values is f of x equal to 5, your answer is going to be an x value. So usually when you're being asked where or when something happens, your answers are x values. And that's really what you can think of on which intervals as meaning. It's kind of saying where or when is this function increasing. Okay, so we're going to go now and actually talk about the next topic, which is local maxima and minima. And then at the end, we'll do an example that reviews everything. So we'll do another example of increasing and decreasing at the end of this video. Okay, so before we talk about local maxima and minima, we need to talk about something called an absolute maximum and an absolute minimum. So I have an example pulled up here. So let me just write this down. So the absolute maximum value of a function is the highest, or maybe let me say it this way, largest y value included in the function. So when you're talking about the maximum value of a function, that's always a y value. Again, think about if this is a graph of temperature or the height of a ball as time goes on. If someone says, what's the highest temperature, or what's the highest height that the ball reaches? What is the maximum temperature? You're not going to tell them an x value. You're going to tell them that output, right? Because the output represents the value of the function, whatever that function represents. So for this example, so let's say this function is called f of x. So the absolute maximum, and I'll probably abbreviate, by the way, the word maximum as just max and the word minimum as min. So the absolute maximum of this function f of x is 9, right? Because that's the highest value that the function reaches. So there's something else we can add to kind of be a little bit more descriptive. We can say that this maximum occurs at x is equal to, -2. So it's a little bit, specific to learn this language, but again, it kind of goes along with what we saw in the last topic. So when you're describing like where or when something's happening, that's your x values. When you're talking about the actual value of the function, that's where you're talking about y values. So one thing that I just want to say, and this is, again, getting a little bit maybe nitpicky, but it is important. It would not be correct to say that the maximum of this function is -2, 9. Technically, that doesn't make sense. Whenever you're asked what is the maximum value, that should be a y value, right? We said it here, it's a y value. If you're asked when or where or at what point that max or min occurs, that's where you give your x value. And again, this will make, I think, a little more sense when we see the next video. Okay, so let's look at an example of the opposite. So some functions also have what's called an absolute minimum. So let's call this function g of x. So the absolute minimum value of a function is the smallest y value included in the function. So in this example, what would be the absolute minimum of this function g of x? Well, it would be -1, right? That's the lowest y value. And where or when does this minimum occur? Well, this minimum occurs at x is equal to 3, because that's the x value corresponding to that minimum y value. So again, it's kind of like if someone said, here's a graph of the temperature after t hours or x hours, and they would say, what's the absolute minimum temperature and at what time does it occur? And so that's why one answer is a y value and the other answer is an x value. So one thing you might notice is that this first function that we looked at, it doesn't actually have an absolute minimum, right? Because we can assume that this graph keeps going. And this function, again, if we assume that it keeps going, this one doesn't have an absolute maximum. So not every function has an absolute maximum or minimum. So there's plenty of functions out there that that either, like these two, have just an absolute max, no absolute min, or just an absolute min, no absolute max. Furthermore, there are types of functions like this one that have actually neither. So some functions have neither an absolute minimum or an absolute maximum, right? This graph, if we were to remind ourselves that it continues off the page, we can see that it doesn't have a very highest or very smallest value, right? It just keeps going. There's no highest point contained in the graph, no lowest point contained in the graph. However, we do have these 2 points that kind of look like a max and a min, right? They have the same kind of shape. Like if we go back to, what does a maximum look like? It kind of looks like this hill, right? It goes up and then it goes back down. And what does a minimum look like? It kind of looks like a valley. It looks like a place where the graph goes down and then comes back up. And so even though this graph does not actually have an absolute maximum or an absolute minimum, it has what's called a local maximum and a local minimum. So a local maximum and a local minimum, those are basically just ways to describe the shape of the graph. It doesn't really have to do with the very highest or very lowest point in the graph. It's really more of a description of a feature of the graph. The way that the graph has this little peak and this little valley in it, that's what is going to be referred to as a local max or min. So let me kind of write this down, and then we'll write down like a more official definition. So this function does, however, have a local max and a local min. So why are we calling this idea of this sort of like peak and valley? Why are we calling it local? Well, if you think about what local means, if someone says, support your local businesses, that means the business is close by. And so basically what you can think of local max and min as meaning is, let's say that you're kind of restricting your graph to this little piece of it. And think of that as kind of like a neighborhood, like right, this is like a local little area, a little zone of our graph. Locally, if you ignore everything else in this picture, well, then we do have a maximum, right? And similarly, if you kind of restrict your graph, if you ignore everything else out here, well, then you do have a minimum. And so that's why the word local is used, because it's kind of like ignoring the big picture and focusing in on kind of a smaller version of the graph. Okay, so I'm going to define for you what a local max and min mean exactly, and then we will actually do that same example a little more precisely, and then we'll do one last example. Okay, let me switch colors. I've been using that same color a lot. So a local maximum of a function is a y value. So again, when we're identifying these, we're always going to be providing the y values as the actual local maximum or local minimum value. So it's a y value that is higher, or let me say it same as I said earlier, I'll say larger than other y values nearby on the graph. So not necessarily the largest point in the whole graph, but like higher than the points nearby. So going back to this picture here, right, we see that this point here, it's not the very highest point in the graph, but it's higher than the other points. Like if you just look here and here, it's higher than the points around it. So I'm going to also write down that it's going to looks like a, I'll call it a peak in the graph, right? Like a mountain peak. So similarly, a local minimum of a function is a y value that is smaller than other y values that are nearby on the graph. And I know you might be bothered by like the word nearby is kind of vague. But it really is meant to be vague because it doesn't matter. It really depends on the graph. As long as you see a peak or a valley happening, it's a local max or min. So even, let me actually finish this sentence and then I'll sketch an example just to show you what I mean when I say that. So if the other one looks like a peak, this is going to look like a valley in the graph. So just to kind of sketch like a quick example of like how, really it can be any size of peak or valley. Let's say you had a function that looked like this. This has a ton of local maxima and minima, right? They're just every time like Here we would have a local max, here we'd have a local min, local max, local min, local max, local min. Like anytime the graph goes up, even if it's just by a little bit, as long as you have that little hill shape or peak shape, it's a local max, and anytime you have that little valley shape, it's considered a local min. And so that's why it just says nearby. It's because it could be really nearby if it's a very tiny hill or valley, or it could be nearby a little bit more generally if it's kind of a bigger hill or valley like in this graph. Okay, so let's look back at this exact same example, but now we're gonna write this down kind of like the correct way. So let's call this function, let's call it h of x, or actually, did we call it something earlier? No, I don't think so. I think we called f and g, so let's call this one h of x. So what we would say is that this function h of x has a local max or a local maximum of 2 at x is equal to -1. So notice that when you're actually saying the maximum, that's going to be a y value. And so that goes with this point here, right? This is where we see that local max. But you wouldn't want to say that the local max is -1, 2. Technically, that's not correct. You know, I would know what you mean, but I want to train you to know how to say this the right way, because this will also come up in calculus, by the way, and I want to make sure you really know the kind of correct way to talk about it. So the local maximum is 2, and that local maximum occurs at x is equal to -1. So similarly, this graph has a local minimum, which h of x has a local minimum of -2, and that value of -2 occurs at x is equal to +1. So here, you know, we have our peak, and here we have our valley, and that gives us our local max and our local min. Maybe I'll add some color so that if you're looking at the notes, you can really tell what's referring to what. Okay, so last thing we're going to do is look at one more example and talk about both increasing and decreasing, as well as local maxima and minima. And then in this example, we'll also be able to say what an absolute max is. So one thing, actually, I'll wait until I get there to say the next thing. Okay, so let's say that this function is, let's maybe go back to f of x and say this is f of x. Okay, so first thing we want to do is we want to figure out on which intervals is this function f of x increasing. So if you haven't already, I would recommend at this point pausing the video and trying this yourself, because now we know all the different terms and it's just a matter of practicing them. Okay, so if we're looking for the graph to be increasing, that means we're looking for the parts of the graph where as you move from left to right, the graph is going up. And so we can see that the graph is going up all the way from starting at -infinity. And where does it stop? It stops at x is equal to -2. And again, we do not include -2 because that's a point where it's doing neither, right? At -2, it's not increasing or decreasing. Maybe this notation will be better. I'll just put like a parenthesis there to really emphasize that's where it stops. Then it starts decreasing, right? So again, this part is not included in either, but it's going down, 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 stops going down. Now it starts going up again, up, 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 stops going up, and then it starts going down again. Okay, so we already said the first interval. So the second interval where it's increasing is going to be from x is equal to 0 until x is equal to 2. Okay, so now we can answer on which intervals is this function decreasing. So now we're looking at the intervals in red, the places where it's going down. And so recording the x values, we have -2 up until 0. So x value of -2, x value of 0. And then the next place where it's decreasing starts at x is equal to 2 and keeps going forever. So decreasing from 2 onward. Okay, so next thing we want to answer is we're going to find all local maxima and minima. So again, remember, maxima and minima is just the plural for maximum and minimum of this function, as well as the x values where they occur. And so we're going to write our answers in kind of the same format as we did in the last problem. So we're going to first say what the y value is and then say it happens at x is equal to whatever. Okay, so let's first look for local maxima. So we're just looking for any time we have a peak in the graph, and we can see that one of those happens here, right? At x is equal to -2, we have a height of 1, and so we would say that we have a local max or a local maximum of 1, right? Because that was our y value, and that happens at x is equal to -2. We also have a local max of 3, and that happens at x is equal to 2. And so you might notice that there's something a little funny about this second one. Notice that this local maximum is also the absolute maximum. And we'll come back to that idea once we do write down the local min. But that's okay. So what I just want to make clear is that anytime you're asked for local maxima and minima, it's just asking for any peak or valley in the graph. It doesn't matter if it's the highest point overall or if it's not. All that matters is that it looks like a peak or a valley in the graph. So it is possible for something to be both a local maximum or minimum and an absolute maximum or minimum. They're not mutually exclusive categories. So they just kind of are referring to different things. Local max or min is just referring to like the shape of the graph, whereas absolute max or min is referring to the overall highest or lowest point. So there is some overlap. Okay, what about local minima? Well, we see that we have a low point here, right? We have a valley at this point. And so that means that we have a local min of, and the y value of that point is -2. And that occurs at x is equal to 0. So yeah, last thing I just want to answer is basically, does this function have an absolute maximum and or minimum? Because as we saw, not every graph has an absolute max or min. And also not every graph has local maxima or minima, but I chose this graph specifically so that it did. For example, if you have like a line, right, a linear function, a line, that's not going to have any peaks or valleys. So not every graph has these kind of features. So we already decided, yeah, it does, right? It has an absolute maximum of 3, right? 3 is the very highest point that this graph ever touches. So it does have an absolute maximum of 3 at x is equal to 2. However, it does not have an absolute minimum, right? Because the graph keeps going down and down and down. There is no lowest value. So we would say that there is no absolute min. All right, so that's it for this video. And I know, we've learned a whole bunch of new kind of terminology and vocab and stuff over the past couple of videos. So as I said, the next video is basically just going to be practicing these ideas, but also adding in some context. So practicing them alongside some kind of real world situations so you can understand a little bit better what is the real significance of finding these sort of features in a graph. All right, I will see you all in the next video.